So what is a limit? A limit in some sense is it's really just describing the behavior of a function near a point or near a specific x value. Not necessarily the actual value of the function, but how the function is behaving around that. So let's write out a few formal definitions and then we'll do some examples and hopefully clarify and explain these a little bit more. So we write lim as x approaches a, f of x equals L. And so we read that as the limit as x approaches a of f of x equals L if we can make the values of f arbitrarily close to L by taking sufficiently by taking x sufficiently close to a. So what does this mean? Sometimes we have functions that are discontinuous. We haven't seen a whole lot in pre-calc, and the only ones we've seen are rational functions. But in calculus, we will often see when we want to compare ratios of functions that sometimes functions have holes in them. And so the thing to note is that our L and of course f of x are y values. So our L is here. And the a and x values are x values. And so what's going on with this function? Well, it's just got one point removed. Otherwise, it behaves normally. And you can kind of see this, think of this as maybe like a statistical function where something's going on and all these points, all the data fits a nice line and curve, but then for some reason there's an outlier. And maybe we just don't even want to consider that outlier. It's just one point. The behavior of the function, aside from that one tiny point, is going to behave in a nice way. And so what do we want to do? We want a mathematical way to describe what is actually going on of the behavior when x is a. Because if we just plugged in a to the function, we would get the value, the y value of that point, which doesn't really describe what's going on with the function near that value. And so what is the limit? Well, we can see that as our x values get arbitrarily close to a, in other words, if we just have a tiny window of x values that we want to consider, then the y values will end up fairly close to L. In other words, the y window, the range of y values that are going to correspond to this range of x values, it's going to be very tiny and essentially very close to L, to the actual limit. Another way we can think about this is in terms of left and right-sided limits. So we often write limit as x approaches a from the left. So we say put a superscript negative on the a to mean x approaches a from the left or from below. What does this mean? This means if I'm tracing the curve from below a, so I pick the x values below a, and I'm figuring out, well, what are the y values doing as we approach and we're getting closer and closer to a, what's the y value we're hitting as we come into the left, as we're approaching a. Likewise, we have notation for what happens when we approach from the right. In this case, we just put a plus as a superscript above the a. And in this case, this just means we want x values bigger than a, and we're looking to the right of a, but we are approaching towards a. And as we get closer and closer to a, what value are we approaching? Now, it can be the case that these two are not always the same. Sometimes the right limit and the left limit are different. And if they're different, then the general limit doesn't exist. So we'll go over that when we do a graphing example. At the moment, let's do an example with a computational device. Let's just get this one out of the way. And let's suppose we have a function g of x is equal to x cubed plus, x cubed minus 8 over x minus 2. And we want the limit as x approaches 2 of g of x. So in calculus, you'll learn more rigorous ways of dealing with this analytically. For our intents and purposes, we're essentially just going to do everything with a computational device. Questions like this will not appear on quizzes, so only use computational devices on WebAssign for the homework problems where it asks you. For the questions on quizzes, they're essentially all going to be graphical, and we'll do an example like that afterwards. So there's only going to be two steps. The first step with any limit problem is to plug in the limit. If it's not a piecewise function. This is just a rational function defined everywhere except where possibly x equals 2. And the first thing we're going to do is try to see what happens when I just plug in that value. What is g of 2? We get zero over 0. This is a new form. So this is called indeterminate. So this is a new word, and it's different from being undefined or not existing. So we've seen things like that in pre-calc where sometimes you try to compute a value, and if the function goes off to infinity or has an asymptote, we usually say does not exist or it's undefined. In this case, we're going to say that it's an indeterminate form. And really, when I'm plugging in this limit, we are plugging it into the original function with the idea that we are actually trying to compute the limit. And an indeterminate form, so the root word means is determined. So indeterminate means we cannot determine it. In other words, we need more info. This type of expression will occur anytime there are mathematical contradictions. And in this case, we have, well, what happens if I take 0, if I have nothing, and divide it by any number? 0 divided by anything should be 0. However, if I have anything and divide by 0, what happens? It's undefined. It goes off to infinity, usually. So we have these contradictions. I have one rule that says this should be 0, and another rule that says it should also be undefined or infinity. So which is it? This is why it's indeterminate. We have these clashing concepts of math going on, and we have to do some extra work to figure out really what's going on. We've got to do some more rigorous analysis. In calculus, you'll learn how to do the analysis with algebra. For this class, we are just going to estimate it with a table. So let's go ahead. We want our x values. The x values have to get close to 2, and we're going to want values below and above 2. So let's have 1.5, 1.9, and then even closer, 1.99. At 2, we cannot compute. It's indeterminate, so we'll leave that one blank. And then we want to pick values slightly above 2 that are approaching 2 to compute. So I went ahead and computed those. So let's just see the numbers and see what happens. When we plug in 1.5, we will get 9.25. When we plug in 1.9, even closer to 2, we get 11.41. 1.99, closer still, we get 11.94. This was approaching 2 from below, from the left. If we approach 2 from the right, what are we going to get? We plug in 2.5, we get 15.25. 2.1, we get 12.61. 2.01, we get 12.06.
Wait, how are you getting these bottom numbers?
Calculator. This will be something like appears on WebAssign.
Gotcha.
Yeah, not on a quiz. Something like this, you will never see these numbers on a quiz. But on WebAssign, you have some problems like this.
Okay, thanks.
So I already got them through a calculator. I don't want to go through the plugging it into a calculator for you. You guys can check those numbers on your own. The key idea is, well, when we want to get closer and closer to 2, we want to pick numbers that are really close, 2.01, slightly above, 1.99, slightly below. And we want to see the trend. What are these numbers getting closer and closer to that should, if we were to fill in a value here, that should be between these numbers as they're squeezing closer and closer to 2, what would the value of the function be? And we see that this is really close to 12, slightly below. And then when I plug in values from the right, slightly above 2, we get numbers, again, that are approaching 12. So by estimation, the limit as x approaches 2 of f of x is 12. And again, sorry, I wrote the wrong letter, of g of x, excuse me. And this was our function. So again, check that on your own if you want. Plug in those values into this function and see if they match up. Now, one of the key points was that the left side and the right side, both of these numbers are getting close to 12. And if we kept going 1.999, 2.001, they would get even closer. There are certain cases where the limit actually does not exist. So let's draw a graph and see how this appears. So let's say we've got something like this. We've got a line, we've got a semicircle, straight line here, and maybe a point up here. And this will be our function, f of x. Let's answer a few things about this function. So what is the limit as x approaches 0 of f of x? So we kind of want to keep the same process. The first thing we should do is check the value of the function. Specifically at 0, what's going on here? The function is continuous at 0. There's no gap, no hole, nothing strange going on. And in that case, the limit, if we trace the curve from either side, it's going to touch the value there, the actual value of the function. So wherever the function is continuous, the limit is the value. Namely, f of 0 is 1. But if we pick a different point, say 1, as x approaches 1, we'll start off with the left-sided limit. So the limit from below means, so here's x equals 1. We want to trace the curve and watch as the x values get closer and closer to 1. What are the y values doing? So the y value we approach is 2. However, if we look at the limit as x approaches 1 from the right, we're approaching 1, but we're approaching from above 1, getting smaller, smaller, closer to 1. And the x value, or excuse me, the y value we approach is 1. So this means, since those two pieces aren't coming together, even if they're not touching, sometimes there's just a hole, but the two pieces are coming right together. When they do come together, the limit will exist. However, in this case, since there's a gap there, the general limit as x approaches 1, we say does not exist. Because the left side and the right side aren't meeting up. So the last one I wanted to mention is, sometimes you'll see just f of 1. No limits here. It says find f of 1. And what does f of 1 mean? It means the value of the function when x is equal to 1. In other words, the y value. So in this case, we're not actually trying to trace the curve. We want to just know what is the actual value of the function. Where is a dot, or where is a solid line? At f of 1, the y value is all the way up here at 4. And so these are our new tools. When we want to study functions like this, we have now a better mathematical way to describe all these different phenomena, the left and right-sided limits, as well as if a general limit exists and whether that is the same or different from the actual value of the function. Any questions?